All right, we're taking a look at writing and balancing chemical equations, the magic of chemistry. If you look at the warm-up, it says water can be broken down into its component elements, oxygen and hydrogen, by applying an electric current. This process is known as electrolysis. Use your knowledge of chemical nomenclature to write an equation showing the process occurring in the diagram. Be sure to indicate hydrogen and oxygen as diatomic molecules. So if you're breaking down water and you know that water has a chemical formula of H2O, we would first include that, and then if we're breaking down into oxygen and hydrogen gases, which are diatomic, we would write O2 and H2. Now, we want to count the total number of atoms of hydrogen and oxygen before and after the change. So we have 2 hydrogens on the left, 2 hydrogens on the right. I have 1 oxygen on the left, and I have 2 oxygens on the right. We need to make any necessary changes to indicate the states of the substances in the equation and include anything else that we feel might be necessary. So this is liquid water, and you are forming gas because you can see these little tiny bubbles. So this is oxygen and hydrogen gas that's forming. And if we want to change anything else that might be relevant, we should probably balance out the number of oxygens because we need to follow the law of conservation of mass. You need to have the same number of each type of atom on the reactant and the product side. So since I have 2 on the right-hand side of the oxygen, I'm going to put a 2 in front of the water to balance out the oxygen, which then is going to give me more hydrogen. So I'm going to put a 2 in front of hydrogen. And these are known as coefficients. So this would be the decomposition reaction for water. Now, let's take a look at the use of chemical shorthand. So chemists use chemical equations to condense a large amount of information into short expressions, and there are 2 different types of chemical equation. There's a word equation, and then there's the formula equation. Now, when you've got mercury 2 oxide decomposing into mercury and oxygen, mercury 2 oxide is a deep red color, and mercury is a silver liquid. And the formula equation sometimes is referred to as the molecular equation. And the starting substances are the reactants, and the new substances formed are the products. And formula equations might be italicized to indicate they may take the physical states of matter here, like the solid and the liquid and the gas, and they might italicize those letters to indicate those states of the reactants and the products. Let's go to the next page here. The symbol S after, in parentheses, after a chemical formula indicates that it's a solid. The script L indicates it's a liquid. A lowercase g indicates that it's a gas. And the symbol AQ stands for aqueous, which means it is dissolved in water. You can tell that a chemical reaction has happened by looking for different forms of evidence that there was a chemical change. Some examples of this evidence would be that there is an absorption or releasing of heat. If it absorbs heat, it's going to feel cold. If it releases heat, it's going to feel warm or hot. And sometimes it might release light. You will see an unexpected color change. The evolution of gas, that means you may see bubbles. If you open up a soda can, those bubbles that you're seeing aren't actually evidence of a chemical reaction. That's the carbon dioxide gas that was in the solution coming out. Sometimes they're going to refer to this evolution of gas as effervesces. And then the formation of a solid when you mix 2 solutions, that solid is known as a precipitate. And a precipitate is often called an insoluble product. Let's take a look at the quick check. List 3 pieces of evidence of a chemical change in the decomposition of mercury 2 oxide. So before I have given you some colors and some different states of matter for the reactants and the products on the previous page. Let's go ahead and go ahead and look at that chemical reaction on the previous page where mercury 2 oxide, which was a deep red powder, decomposed into mercury, which is a liquid, and it's silver in color, and then you're producing oxygen gas. So oxygen gas is produced, so that's a form of evidence. And you get this gas information from the state of matter in the formula equation on the previous page. There's going to also be a change in mass because when you lose, when the oxygen gas leaves, the mass is going to change. Number 3, there was an unexpected color change. You went from the deep red color to the silver color. Number 2, convert the following from a word equation to a formula equation. Calcium oxide powder is combined with water to form calcium hydroxide solid. So calcium oxide powder, that's going to be Ca plus 2, O minus 2. The numbers and the charges cancel. You get CaO, and that's a solid because it's a powder. It's combined with water, which is H2O, and that's a liquid. You're forming calcium hydroxide solid. So this is Ca plus 2 for calcium, OH minus 1 for hydroxide. You cross the charges. Hydroxide's in parentheses with a subscript 2, and then you put the solid state of matter. Number 3, convert the following from a formula equation to a word equation. So H2CO3, this is an oxy acid. This CO3 is named carbonate. Remember, when you have an 8, it becomes an ic acid. So this is carbonic acid. And it's decomposing into carbon dioxide, gas, and water. You could say, since this is a liquid, you could insert that this is liquid water. Now let's move on to balancing chemical equations. Antoine Lavoisier liked to measure the volumes and masses of chemicals that he studied. He is credited with formulating the law of conservation of mass. This states that the mass before and after a chemical reaction occurs remains constant. And if we turn to the next page, if we look at the decomposition of mercury 2 oxide, it shows that it does not obey the law of conservation of mass. But to show that the mass before and after, let me pull this down here. To show that the mass before and after a chemical reaction occurs remains constant, you have to balance the equation. So if you're looking here at this mercury 2 oxide decomposition reaction, you see that you have 1 mercury on the reactant and the product side, but you have 1 oxygen on the reactant side and 2 oxygens on the product side. So the oxygens are not balanced. So it requires that we put a coefficient in front of the reactant. And sometimes you have to put a coefficient in front of the product to balance it. So if I put a 2 here, that will balance the oxygens. And then I have 2 mercury, so I have to put a 2 in front of mercury as well. So my coefficients here are 2, 2, and then 1. So the coefficients multiply the entire chemical species that follow them, and those numbers ensure that the number of atoms of each kind on the reactant and the product side are equal. We cannot change the subscripts. Never change the subscripts, because if you change the subscripts, what that does is it gives you a completely new substance. So let's take a look here at the quick check. You'll notice that in number 1, I have a sodium on each side of the arrow. I have 2 chlorines on each side. So this is a properly balanced equation. So we would circle this one. I believe this example is different from the example in your book. I believe A in your book is not balanced because you only have 1 chlorine on the right and 2 on the left. If I'm looking at B, since you have polyatomic ions in B, you have nitrate. I'm going to put those in boxes, and I'm going to balance those as groups. I have a silver on each side, a NO3 on each side, a K on each side, and a Br on each side. So this one is balanced. In C, I have 2 hydrogens on the reactant side, 4 hydrogens on the product side. So this is automatically not balanced, so I'm not going to circle it. For D, I have 3 carbons on the left, 3 carbons on the right, 8 hydrogens on the left. 4 times 2 gives me 8 hydrogens on the right. You have 10 oxygen on the left. You have 6 oxygen in this compound here, plus another 4. So 6 plus 4 oxygen give me 10. So this is balanced as well. For E, I have 3 lithium on the left, 3 lithium on the right. Hydroxide is a polyatomic ion, so I'm going to put it in a bracket. I have 3 hydroxides on the left, 3 hydroxides on the right. I have 1 iron on each side. IO4 is a polyatomic ion, so I'm going to put that in a bracket as well. I have 3 IO4s on the left, 3 IO4s on the right, so this is also balanced. Now, let me give you a few hints on balancing. You begin balancing atoms that appear in only one place on each side of the equation. And the atoms that appear in too many places are more difficult to balance, so you should leave those until the end. Oxygen and hydrogen often appear in multiple places. Balance atoms that occur in elemental form last. That means if you have pure oxygen or pure hydrogen, balance things like that last. You want to balance polyatomic ions as groups. So this would be things like nitrate, sulfate. And once a coefficient is placed in front of a molecule, you want to finish balancing the rest of the atoms in that species before moving on. Let's take a look at the next page. Let's look at this sample problem here. You have a barium on each side, an aluminum on each side, and you have a nitrate polyatomic ion on each side. You have 3 on the left and 2 on the right. The lowest common multiple of 2 and 3 is 6. So I'm going to put a 2 in front of the aluminum nitrate because 2 times 3 would be 6 nitrate. If I put a 3 in front of barium nitrate, 3 times 2 is 6. So I just balanced my nitrates on each side. When I put my 2 here in front of aluminum nitrate, now I have 2 aluminum, so I need to put a 2 in front of the aluminum on the right side. This 3 in front of the barium nitrate gave me 3 barium, so you put a 3 in front of Ba, and your coefficients are going to be 3, 2, 3, 2. Let's move on to another sample problem here. For this one, we have 2 sodium on each side. And I have a hydroxide here. And I can't balance that with a hydroxide on the right side because I sometimes can rewrite water as HOH and balance it as a hydrogen with a hydroxide, but in this case I can't because I don't have a hydrogen separate from a hydroxide. So that gives me 2 oxygen here, 3 oxygen here, 2 oxygen here total. I'm going to wait on balancing that because I've got 2 chromium in the Cr2O3. So I'm going to put a 2 here in front of the Na2CrO4, which then changes my sodium. So when I balanced my chromium, I now have 4 sodium on the right side, so I'm going to put a 4 in front of Na. Then what I'm going to do is I'm going to take a look at, I have 4 hydrogen here. I have 2 hydrogen here, so I'm going to put a 2 in front of H2O. And I want to balance this O2 last because it's pure, and it'll just make life a lot easier. So here's my 4 hydrogens. And then in terms of oxygen, you have 4 oxygen here, 3 here, which is 7, 2 here, which is 9. On the right-hand side, I have 8 oxygen from this compound, plus 2 here. So I have 10 oxygen on that side. So what I'm going to do is, if I want 10, and I have 4 plus 3, which is 7, and this is 9, if I can somehow put a fraction in front of O2, and I can eliminate that fraction by multiplying all the coefficients by a common number, then that would help me balance it. So what I'm going to do is put a fraction 3/2 here, because if I do that and I multiply this entire equation by 2, then this coefficient becomes an 8. This coefficient of 1 becomes a 2. This coefficient becomes a 3. This becomes a 4. And this becomes a 4. And that will actually give me a balanced equation. So now everything is balanced. I have 8 sodiums, 4 times 2 is 8. I have 8 oxygen here, 6 here. So that's going to be 14 plus 6 here, which is 20. So you have 16 plus 4 oxygens, which is 20. I have 4 chromium on each side, and it looks like I'm balanced, 8 hydrogens on each side. Okay, so that's a more challenging problem for balancing. Now, let's take a look here at the practice problems. I'm going to skip practice problem number 1, and I'm going to go to practice problem number 2. Now, when we're balancing, you want to have the smallest possible ratio of whole number coefficients in front of all of the different substances. So here we have a sulfate on each side, which is a polyatomic ion. So I'm going to balance this first. I have 3 sulfates on the right, so I'm going to put a 3 in front of H2SO4. This 3 times 2 gives me 6 hydrogen. So I'm going to put a 3 in front of H2 to give me 6 hydrogen. Then you have 2 aluminum here on the right, so I'm going to put a 2 in front of the aluminum on the left. And now I am balanced. My coefficients are 2, 3, 1, 3. For B, I have a hydroxide, which is a polyatomic ion on the right-hand side. And then I've got a hydrogen separate. So what I could try and do is rewrite water as HOH. This is when you have a hydrogen separate from a hydroxide in a compound. You can rewrite water as HOH and balance it as a hydrogen attached to a hydroxide. So what I mean is I have 2 hydroxides here, 3 hydrogen here, the lowest common multiple is 6. So if I put a 3 in front of the MgOH2, 3 times 2 is 6. If I put a 2 here, 2 times 3 is 6. So now I have the same number of hydrogens and hydroxides. So I would put a 6 in front of the HOH to give me 6 hydrogen, 6 hydroxide. You have 3 magnesium on each side. You have 2 nitrogen on each side. So your coefficients are 1, 6, 3, 2. For C, I've got no polyatomic ions that I can balance out separately. What I'm going to do is I'm going to take a look first at my hydrogens. So I've got 2 hydrogen on the right, and I have 3 hydrogen on the left. So if I go ahead and try to balance this by putting a 2 in front of NH3 to give me 6 hydrogen here, and a 3 in front of H2O to give me 6 hydrogen here. This 2 gives me 2 N's. I'm going to put a 2 in front of NO to give me 2 N's. I'm going to balance this O2 last. So now I have 3 oxygen in H2O, 2 oxygen in O, 3 plus 2 is 5. When there's an odd number that you want, put that odd number in front of the O2 and then put it over 2. And the reason you do that is because if you multiply all of the other coefficients by 2 to get rid of this fraction, this becomes a 4, this becomes a 5, this becomes a 6, and this becomes a 4, and now everything will be balanced. Let's take a look at the next page. Let's look at this sample problem. Here we have butane, which is a hydrocarbon, burning in oxygen to produce carbon dioxide and water. The formula for butane is C4H10. So this is a combustion reaction. This is your hydrocarbon, which will always be given to you, and then it will always react with pure oxygen to give you carbon dioxide and water. Now, when you're balancing a combustion reaction, you want to balance the O2 last. So you have 4 carbon on the left, so you would put a 4 in front of the CO2. You have 10 hydrogens on the left. You have 2 on the right, so you would need a 5 in front of H2O. Then you would count up how many oxygens are on the right. You have 8 oxygen in this compound, 5 here. 8 plus 5 is 13. That's an odd number of oxygen. So put the 13 in front of the O2 and put it over 2, because you need to multiply the entire equation by 2 to get rid of that fraction. So 2 times this 1 in front of C4H10 would give you 2. 2 times 13 halves would be 13. 2 times 4 would be 8. 2 times 5 would be 10. Let's take a look at the practice problems here. We're going to write balanced equations using the smallest possible whole number coefficients, and we're going to include phase indicators or states of matter. Solid iron, so that would be Fe with a little s after it. Chlorine gas. Chlorine is diatomic, so it's Cl2. These combine to form iron 3 chloride. So iron 3 chloride comes from crossing the charges. You get FeCl3. Now, if I need to balance this, I'm going to look at the chlorine. 2 and 3 are my subscripts. The lowest common multiple would be 6. So I would put a 3 in front of the Cl2 and a 2 in front of the FeCl3. Now I need to put a 2 in front of Fe, and that's my balanced equation. Number 2, aqueous solutions of ammonium phosphide. So ammonium phosphide comes from NH4 plus 1 and P minus 3, where you cross the charges. And this is a solution, so you put an AQ after it. We're combining it with lead 2 bromate. So we cross the charges, you get PbBrO3 subscript 2, and that's a solution, so you put an AQ. Those are reacting to give a precipitate, which is a solid, lead 2 phosphide, and that's going to be Pb3P2, so I put a solid after that, and aqueous ammonium bromate, which is NH4BrO3. Now we have to balance it. So I have 3 NH4s on the left, and I have 1 on the right. So I'm going to put a 3 in front of NH4BrO3. Unfortunately, you have 2 BrO3s on the left, so we need to make this a 6. Put a 3 here to make this 6 BrO3s. Let's change this coefficient to a 6 to give me 6 BrO3s. Then you have 6 NH4s, so I'm going to put a 2 here because 2 times 3 would be 6. You have 2 phosphorus on each side, 3 leads on each side, so you're done. Your coefficients are 2, 3, 1, 6. Number 3, calcium metal, so that's calcium with solid state of matter, reacts in an aqueous solution of nickel 3 sulfate. Sulfate has a -2 charge. The charge on the nickel crosses over onto the sulfate. Since that's a solution, put an AQ after it. It's forming calcium sulfate, which is CaSO4. They say that's a solution, and nickel metal. Now, if I have 3 SO4s on the reactant side, put a 3 over here to balance out your SO4s. You have 3 calcium, so put a 3 in front of calcium. You have 2 nickels on the left, so put a 2 in front of the nickel on the right. Your coefficients are 3, 1, 3, 2.